Hello, everyone, and welcome to today's webinar, DualEELS, the importance of low loss correction of electron energy loss spectroscopy data. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we'll follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. Dr. Liam Spillane has been working in the field of electron microscopy for the past 17 years. He started his career as a PhD student at Imperial College London, studying oxide thin films using aberration-corrected stem and monochromated EELS. After completing his PhD, he worked as a postdoctoral research assistant in advanced electron microscopy, working on the structural and chemical characterization of materials across a number of projects, including nanoparticle toxicology, ferroelectrics, nanoparticle catalysts, and solid oxide fuel cells. After leaving Imperial College in 2012, Dr. Spillane joined Gatan, initially working with the UK Sales and Service Group for a number of years. He relocated to Gatan, USA in Pleasanton, California in 2018, where he is currently the application scientist for Gatan's STEM, EELS, and GIF products. Now over to Liam.
Thanks, Jonathan. Okay, and yeah, thanks everyone for joining the webinar. So let's get going. Okay, so the webinar is about DualEELS processing. So let's start off with some fundamental aims of quantification. So what do we want to do when we're doing elemental quantification? Essentially, we need to identify, extract, and quantify element-specific information from our energy loss spectra, and we need to convert that spectrum into meaningful analytical quantities. So primarily when we're doing quantification, we're targeting features in the core loss region of the spectrum, so ionization edges, right? So we can ask ourselves the question, why acquire the low loss spectrum? So there's many reasons why we would acquire the low loss spectrum. So it contains lots of really useful additional information. So we have information about the valence state, band gap information about specimen thickness, zero loss intensity, vibrational information, and so forth. It also contains information that's useful for us to process our core loss data. So we need the low loss information to do absolute quantification. If we want to calculate areal density, we need the zero loss intensity as well as our edge intensity and our scattering cross-section. It's also critical for an energy scale reference. If we want to do anything like accurate chemical shift measurements, we really need the low loss spectrum. But yeah, also it's really necessary to remove plural scattering. We need to recover the single scatter distribution, and this allows us to do improved quantification and edge separation. So it's this final bullet point which is really going to kind of form the basis of this talk. So what is plural scattering and how do we deal with that? So the effect of plural scattering on core loss edges. So essentially, plural scattering causes a redistribution of our core loss intensity. So what that kind of looks like is a convolution of our single scatter ionization edge. So this figure down here on the left, convolution of this guy with our low loss spectrum. And that redistribution of intensity gives us additional intensity that's not really computed in our calculated cross section. So we have this erroneous intensity that doesn't really relate to how much of the element that we have, and it will also affect the relative peak intensities in the LNES region of that spectrum. So it invalidates the computed cross-section and standards that we're going to use for quantification. So that's quite key. It'll also reduce the signal to background ratio, so our detection limits are going to be kind of off. So how do we do quantification in kind of current generation software, so DigitalMicrograph 3? So there's done with this model fitting approach. So our signals are extracted by model fitting. So we essentially deconstruct the real spectrum into multiple components. So they are the ionization edge and a background model. So a background model is typically a power law model that's fitted in this pre-edge region, just preceding any ionization edge that we're interested in. And then our edge model is usually a simple calculated cross-section. So Hartree-Slater cross-section models are what we're using. So these are the two components that we use for the fit. And then that fit is essentially applied over a fit region that encompasses some background area and some ionization edge area. And we're really kind of extracting data from the fit coefficients that get derived from this fitting. This procedure is repeated for each edge group. One of the real advantages is that it can deal with overlapping signals. So this is kind of a step beyond what can be done with just simple background subtraction. One thing that we do need to be aware of and be careful of is that when we're doing this fit-based quantification, the accuracy of the quantification really directly relates to the accuracy of the fit. So our quant result directly correlates to how accurate and good our fit is. So essentially we need that fit to be as good as possible. So this is really where the plural scattering correction comes in. The plural scattering correction in this model-based approach is done slightly differently. So it's actually incorporated into the cross-section model and not removed. There's a couple of kind of side benefits here. So by doing a forward convolution, we get a noise smoothing effect instead of a noise amplification effect that we would have by deconvolution if we remove the plural scattering. But ultimately, what we're trying to do is just make our edge shapes, our edge models better and improve our fit. One thing that's key here to do this requires the low loss. So this really needs to be done with a DualEELS acquisition. So what we're looking at here is an example, again, from boron nitride. And this is with plural scattering correction essentially off, disabled, not applied. So you can see we have kind of two models, kind of two edge groups here, separate fits for boron, separate fits for nitrogen, and we have a background model for our boron, background model for our nitrogen, and then two Hartree-Slater cross-section shapes for these K edges. And what's quite clear is that the fit isn't super great in this kind of EELS region here, not necessarily because we're not fitting the EELS peaks, it's just that the kind of overall edge shape in this cross-section model is heavily weighted towards the onset area in this K edge. And that's kind of not true to reality because we know that we redistribute our ionization edge intensity to higher energy losses because of the plural scattering. So what happens when we switch on plural scattering correction? So the fit is much improved. So it brings down the intensity in the kind of the near EELS region, I'm going to call it, and then we kind of improve the shape in this kind of higher energy loss region here. So we're not fitting the EELS peaks. We know that we can't do that with these cross-section shapes, but this kind of modified shape with this plural scattering convolution fits the overall edge shape much, much better. So we fit the boron better in this kind of region that's like 240 to 280 EV in this case, and kind of a more true shape also for the nitrogen. Okay, so I've kind of mentioned a little bit about the EELS peaks, and we do not deal with the EELS with these calculated cross-section shapes. But if we do want to deal with the EELS and have the ultimate fit, what we do is a standards-based EELS quantification approach. So this is really nice. It's an extension of the model fitting quantification, but we have two components of the edge shape, the edge model. So we have an experimental part, an experimental kind of edge shape, and we keep our Hartree-Slater cross-section shape, and that's used at higher energy losses, and essentially these two shapes are spliced together. So what this allows us to do is it allows us to fit in the EELS region whilst also kind of being able to do the full analytical quantification that we can do with the Hartree-Slater cross-section model. So essentially we are scaling our measured edge shape to this cross-section model, and that allows us to go and calculate areal density, volumetric density, and so forth. So there's two massive advantages of doing this. We get a superior fit because we're able to fit accurately in a region that we previously couldn't fit at all. And then we can go a step further than just the simple cross-section shapes. We can do quantitative L-ness mapping. So we can do full quant of different phases of the same element or oxidation states and so forth. So how does plural scattering correction factor into the standards-based approach? Okay, so it's pretty similar. So here's an example of standards-based quantification with plural scattering correction. So this is a DualEELS data set that was just acquired from some commercial cobalt oxide powder. And the particles of this powder essentially have a really steep thickness gradient from the edge to the bulk of the particle, which is quite typical. So what we're looking at here is the low loss spectrum image on the left and a relative thickness measurement or map that's derived from this low loss spectrum image. So you can see that the thickness gradient is massive, so very, very thin on the edge, but in this white area in the bulk down here, we're looking at probably thicknesses or relative thicknesses of in excess of 2 lambda. So if we look at some spectra that are extracted from the DualEELS data set, you can see the difference. So we're looking here at plural scattering correction off versus plural scattering correction on. And we're targeting an area where the average lambda or the average Fieva lambda is 1.5. So it's quite thick. If we zoom in, it's pretty clear the difference. So if you look on the left, you can see that without the plural scattering correction, the fit really isn't good. So we don't fit in the area where we expect to see plural scattering at all. That can have kind of two effects. So we can end up with a weird kind of weighting of standards that we're using. So I'm using 2 references here for cobalt, different oxidation states. We'll explore that in a bit more detail later. And we can also see that the pre-edge model is just wrong. So this fit really isn't good on the left. Compared to with the plural scattering correction on, so it's perfect. So it's really key to have this correction applied. If we don't do this correction, it's really hard to make meaningful statements about the data, even for a single spectrum. If the thickness is actually changing, then it's even more important. Okay, so it's pretty much the background of plural scattering and why it's important and why we need to deal with it. Now we'll move on to some slides about the enabling technology and software that we use to go about this. So the enabling technology is essentially it's DualEELS is our solution. So we're able to get 2 spectra near simultaneously as part of a single acquisition. So there's a few pieces of hardware that make that possible. So we have 3 ultra-fast electrostatic devices. So we have beam exposure control down to 100 nanoseconds in the continuum. That's done with this electrostatic beam blanker. So that's the first element in this system. Second electrostatic module is our fast electrostatic drift tube. So that can apply energy offsets up to 2 kV with a 10 microsecond switch time. So that's pretty fast switch time. And then right at the end of the filter optics, kind of after everything and just before the camera, we have another deflector module which applies lateral spectrum shift control. It allows the spectrum to be moved to different parts of the detector right at the end of the filter. So these 3 elements work as a single unified system, and it's really controlled with some fast FPGA kind of programmable electronics. So these kind of individually, we need all 3 of these. They're kind of greater than the sum of their parts. It's a unified system with these 3 components. So that's kind of the hardware in the spectrometer. How does the readout actually work at the detector level? So this is a schematic of how the DualEELS mode works on continuum. So we have independent exposure time of low loss and core loss spectra. And as I've said, it's just a 10 microsecond energy offset between our low loss and our core loss readout. So the camera or part of the camera is exposed to a low loss spectrum. So we collect that low loss spectrum. apply an energy shift with the drift tube, and then this non-dispersive deflector is used to move the readout to a different part of the camera, so we collect the high loss. While that high loss is being collected, we're reading out the low loss. And then as the high loss is being collected, we're basically alternating between these two. So it's kind of like collect, read, collect, read, collect, read. And this happens near simultaneously. So we get these spectral pairs in the software as we're doing this readout. And what we see is essentially data coming in at the same time. We get a pair of spectra instead of just a single spectrum. So this is the readout mode on the fiber couple camera. We have similar readout modes on the other supported cameras. So we can ask ourselves the question, when should we do DualEELS? So these are the camera frame rates for all of the detectors on the continuum. So we're looking at the very fastest end, where 9,000 frames per second with the Stellar, we have 110 microseconds for a single frame on that camera. K3 single frame, we're looking at 333 microseconds. So if we want to go at our maximum frame rate, so single counted frames or single camera frames for a single spectrum, those are our frame rates, okay? But even if we're going that fast, the energy shift control is still, remember, only 10 microseconds. So that shift is very, very fast with respect to all of those camera readout times. And that's really critical, so that essentially what we're presented with is a scenario where our dead time due to our energy shifts is really minimized. So unless we're chasing ultimate time resolution or ultra low dose conditions, really we always want to use DualEELS. We're not really paying a dead time penalty to use DualEELS on the continuum. And the benefits that we get from having the low loss spectra with the core loss spectra really outweigh this significantly. So always use DualEELS if possible. It's super beneficial to have that zero loss peak and low loss spectrum for any downstream processing of the core loss data. So that's the hardware. Like, how does it work in software? So it's pretty simple. So our EELS palette is here on the left, and right at the top we have a button that says single, and we can switch that to dual. What happens when we enable dual mode? So we just get 2 parameter sets instead of 1. So we can choose a low loss energy offset, a high loss energy offset independently, and we can choose 2 frame exposures. So in this case, it's a low loss spectrum that's 10 microsecond exposure and a high loss spectrum that's 2 millisecond exposure. So it's very versatile, very simple. Okay, so here's a walkthrough of how we might go about setting up an experiment and some results on kind of a real system. So this is an experiment that was done on a lunar glass sample. So interested in mapping different oxidation states in this sample of iron. So this workflow is that we would acquire an ADF STEM image, define a spectrum image acquisition area, so this green box here, and we could use drift correction if we wanted, but that's not necessary. The critical thing is we kind of draw an array that we're interested in getting spectral data from. We will get an ADF signal from that array as well as EELS data. And the way that we set up our EELS experiment is just as I showed on the previous slide. So we stick DualEELS mode on, choose low and high energy offsets. So in this case, they're targeting the iron L23 edge, a few milliseconds exposure for the high, and then a fast exposure for the low. And then something that's really nice here, we have ZLP lock, so we can do a live energy calibration as that data is being acquired, which is a neat feature that you can do with fast DualEELS. Okay, so our energy scale is corrected, and we're confident of our energy scale. So what we can do is measure chemical shift. So what they're looking at here is the iron L23 edge, as I just said, comparing kind of the glass matrix here versus these inclusions. And what they found is you have this kind of low oxidation state iron in the inclusions versus high oxidation state iron in the bulk matrix of the glass there. And that can be mapped out. So you can get this nice kind of ion phase maps in this material. What's really kind of impressive with this experiment is they actually did tomography, like EELS tomography. So they did a full tilt series from minus 60 degrees to plus 60 degrees with an interval of, 6 degrees tilt. And here, like, we can think that the relative thickness of this sample is going to change with tilt angle. So it's really important here that we have thickness correction that's applied, and you can do something quite fancy like this, where we get this nice 3D reconstruction of these iron 3 rich kind of inclusions in this glass matrix. Okay, so let's kind of switch gears a little. I wanted to just kind of show you a walkthrough of how we look at DualEELS data in practice. So this is just some pre-acquired data that I have in DigitalMicrograph open already. So what are we looking at? So we're looking at a copper oxide particle that is sitting on a MEMS chip. So this is a MEMS heating holder, MEMS-based heating holder, and this was part of a heating experiment. So the goal really was to measure oxidation state changes in this sample as the temperature is increased. But this data is actually at low temperature, so we're not expecting massive changes. So the data is organized as a compound document. So we have everything that's acquired as part of the capture is in a single container. So we have our STEM survey image. So that's what we're looking at here. If I click scan, that's the ADF data that was acquired as part of the spectrum image capture. EELS low loss, EELS high loss. So we have a bunch of data that is within this kind of bigger group, and that's really useful. So the software knows this is all linked, keeps it compartmentalized, and makes the processing super easy. So if we want to extract some spectra, super simple, we just use the picker tool, right click there, and then draw our picker region and get the sum of all the energy loss spectra from that region there. So if I zoom in a bit, you can see that we have some ionization edges present. Obviously, copper oxide, we're expecting copper, oxygen, and then silicon nitride. So we also expect nitrogen and silicon. So let's just take a little quick look at the low loss spectrum. So this was done with ZLP lock on. So the energy drift is removed already. So the zero loss tracking is good. And if we want to see the thickness of this guy, all we need to do is just select that spectrum and just go over to the EELS analysis palette and hit thickness. So I can see that the thickness is changing quite significantly of this spectrum, or the sample. So right in this like thin area here, we're looking at T over lambda of 0.3, 0.4, and in the center 1.5. So this is, as we fairly typical for this kind of particle. Tends to be thin on the edge, thick in the middle. What does that mean for us in our high loss? So we can just hit the high loss and just quickly look at the copper edge. So I can just zoom into copper, draw an ROI in front of my copper, and then go back to the same palette, hit deconvolve, and I get a live deconvolved spectrum. So what we're looking at right now is the raw spectrum in the kind of solid teal. The green is our raw extracted signal, and then this pink overlay is essentially our single scattering distribution spectrum that is being recovered from this Fourier ratio deconvolution. So if I just move that picker around, that calculation gets kind of redone, and you can see what's the take home here is if I move to the thicker areas, it's really, really clear that the plural scattering correction or plural scattering contribution to the edge here is like very, very different to the kind of the thin areas on the edge of the sample, and that's kind of what we need to deal with. Right, so that's just kind of the quick and easy way of looking at that. Generally, we want to do mapping with these samples. How do we do that? So we just switch off our deconvolution. I'm just going to tidy that up. And I can just go to my elemental quantification palette. So I already have something saved for copper oxide. So I can just do copper oxide standards, load that. I have oxygen and I have copper, and I have essentially I'm doing standard space quantification in this approach. So I'm using two standards for copper. One is for copper 2 and one is for copper metal. So if we want to see how that looks, we just click on the edge setup button and then go to copper, and you get this overlay. Now, this looks great straight away. The reason that looks great is if we look, the checkbox here that says include plural scattering is already enabled. So the software knows that we have a low loss spectrum or a low loss spectrum image. So it's automatically going to apply this correction for us if the data is there. So we don't have to worry about that. It's just out of the box, it's done. What happens if we turn that correction off? Okay, so at the moment it is using mostly the 2+ reference, which is correct. If I turn off the plural scattering correction, essentially the way that the software can get the best fit is actually to have a mixture of the metal reference, which is the darker, as well as some of my 2+, and that's just wrong. So, you know, we're going from a scenario where the plural scattering correction is on and it gives you something that's meaningful to something that is potentially misleading. So it's going to say like, oh, I have a mixed 2+ and 0+, but it's really just that it's trying to use this 0+ reference to fit the plural scattering correction better. So that's something that we need to be careful of and not do. Make sure that the plural scattering correction is on. Final benefit of having the plural scattering correction and the 0 loss is if we go to map, we can see that we have additional parameters here. So if we didn't have the low loss, we would only be able to do edge integral maps or elemental composition maps, so relative percentages. But we can do full analytical quant here. So we can extract areal density, we can extract volumetric density. Okay, so that's pretty much all I wanted to show with the software. So we can go back to PowerPoint slides, and the final elements of the talk that I wanted to show are some application examples. So just a couple of data sets that we have worked on where plural scattering correction was deemed to be pretty important. So the first of these is this data that was acquired from nanoparticles of silicon that are coated with molybdenum disulfide. So this is interesting, right? So this is a 60 kV counted EELS data set, so it's at low kV. The reason that this is done at low kV is the primary damage mechanism for the moly disulfide here is knock-on damage. So we want to be below the knock-on damage threshold. Kind of downside of working at low kV is the inelastic mean-free path is shorter, so we get more plural scattering. Okay, so our samples need to be relatively thinner for us to do analysis. With this particular sample, it's actually particularly challenging because of the geometry of the sample itself. So it's spherical, so we have a relatively kind of a thin area on the edge versus a pretty thick area in the center. What we want to do in the analysis is actually compare the chemistry at the edge versus the chemistry in the bulk. So that's that could be problematic. Okay, so why is that problematic? Okay, so the geometry of the nanoparticle means that we have a huge change in thickness from the edge to the center. So we can look here at the extracted spectra from the nanoparticle. So we have a relative thickness in the center of 1.65 T over lambda versus 0.55 at the very edge of that nanoparticle just through that moly disulfide layer. So we're looking at like approximately 3x difference in thickness. Not surprisingly, the plural scattering contribution difference for these spectra is like significant. So look at the core loss spectra. So we have silicon L, molybdenum M, kind of in our target region here. This green area in the top spectrum is all plural scattering. So this is like going to be super misleading for us if we want to make meaningful kind of analysis of this data. So it really like if we did any quantification, we'd be including all of this intensity. which would be wrong, and it really screws up any kind of peak measurements that we want to make in this area. So we really need to be able to deal with that, and DualEELS is really the solution that is best for this. So this is a low loss example. So the final example I want to show is a high loss example. So I think this was done at 200 or 300 kV. So we're interested in looking at oxygen involving oxide catalysts. So this catalyst, BSCF, is critical in defining basically this oxygen exchange reaction. So what we're interested in is the surface oxidation state of cobalt in this material. This is pretty tricky, okay? So we're looking at two oxidation states of cobalt, so cobalt 2 and cobalt 3. It's also in the presence of barium. So we have barium and cobalt edges, huge overlap. So we have to deal with this with standards. It's really the only approach that we can take to deal with this analytically. So we have concurrent standards, so different references for cobalt. So a nice cobalt 3+ reference, a nice cobalt 2+ reference, and then a standard also for barium. So we're able to separate those three overlapping signals. Now, there's something else that's also key to this. So this is the geometry of this particle is as we've seen for all of the other kind of particle-based samples that I've shown. So we have obviously vacuum area here. So this is not the same sample, but it's representative data. And we have this thin area on the edge, and we're going into somewhere that's like significantly thicker in the bulk of the particle. Whenever we're doing spectrum images or kind of chemical profiles on the edges of these particles, as we've seen from the previous slides, if we don't do plural scattering correction, it really kind of can throw off our measurements or our conclusions significantly. So it's really key that as well as kind of doing this standards-based quantification and analysis for samples like this and systems like this, we have to do plural scattering correction. Otherwise, that analysis really is going to fail. Okay, so that's kind of the last example that I wanted to show. And just a summary slide to recap. So low loss spectra really must be acquired with all core loss data to enable energy calibration and plural scattering correction. Plural scattering correction is really fundamentally required for model-based and standards-based EELS quantification. If you don't do plural scattering correction, you're really not getting the full advantage of doing the quantification by these methods, and you can end up with just results that are wrong or misleading. DualEELS enables low loss and high loss EELS spectral pairs to be acquired at high throughput and collection efficiency due to high speed electrostatics that synchronize with an advanced flexible FPGA technology. And then all of that is super easy. DigitalMicrograph maximizes DualEELS utility through powerful and easy to use software integration. So we don't really need to deal with the complexity of the hardware acquisition. We just get the data and the tools that we need to do the processing. So yeah, so one thing, so thanks everyone for paying attention and listening. And then as a final slide, if anybody is interested in some of the kind of the finer details of model-based EELS quantification and standards-based quantification, we actually had a dedicated webinar on that sometime in the past. So some of the details that I've not provided in this webinar are in the previous webinar. So if anybody wants to watch that, it's on our YouTube channel. Here's a direct link. If you just go to YouTube though and search this title and Gatan, it will probably be one of the top hits in the search field. And then there's also shorter tutorials on how to use the software features if you don't want to watch the full webinar. And yes, so search for standards-based EELS quantification. And then there's two short videos here, one for internal standards and one for external standards. So yeah, so I guess that's the end of the presentation, and it's probably a good point to take some questions if there are any questions.
Well, thanks a lot, Liam. That was a really great presentation. Hi, everyone. This is Ray Tweston. I'm the product manager for Analytical here, and I've been enjoying this presentation as well, but also trying to keep up on the questions that are coming in. Yeah, Liam, we did have a couple of questions. One astute watcher noticed that you were using DigitalMicrograph 3.6 and wanted to know if these features are also in the version that they have. I think they have 3.4. I think they mentioned 3.4.3. Well, DigitalMicrograph 3.4.
Yes, good observation. So yeah, the software features, all the software features that have been discussed and everything that I shows with my software installation is all included in DigitalMicrograph 3.4 and higher. So none of these are kind of unreleased tools. They've been released and available for quite some time.
Great. Yeah, I think 3.6 should be out in the summer of this year, and there are some really interesting new features in there that we'll highlight later. In most, you know, for most people, it's an automatic free upgrade. You just need to get that from your local service group and or download the version. Question also about DualEELS. If I understand, for high energy loss edges, the question was they have an edge that's greater than 2 kilovolts, but the deflector only goes up to 2 kilovolts. Can you still do DualEELS on those edges?
That's a good question. So yeah, so bear in mind when we're doing any kind of EELS acquisition, we have the full energy range of the detector. So it's also dispersion specific, the energy range that we have. So at the lowest dispersions, we have a close to 3000 eV energy range for a single spectrum. So if you couple that with the maximum energy offset that we can do for the DualEELS, we can do 2000 EV energy offset. So the maximum range that you could go from 0 up to max would be something like 5000 EV. So we can, you can go over quite a big energy range. And then you don't have to do low loss if you didn't want. You could do 2 high loss acquisitions. So it would be possible to, or the constraint is just that the low and the high need to be separated by no more or up to 2000 EV. The low doesn't have to be 0. However, if you don't have the low loss, remember that you won't be able to do all of the processing that I've been kind of discussing. So we wouldn't have the 0 loss peak, and you wouldn't have the low loss spectrum, which might be disadvantageous.
Great. Actually, we just got a very related question. If you have an edge that's down at low energies and an edge at high energies, how do you do the mapping in that case, since one would be in the low loss spectrum image and the other one would be in the high loss spectrum image?
So you could splice the data together. You can also map. You can map from the low loss spectrum. We just typically map stuff from the high loss spectrum. But if you choose to map ionization edges that are in the low loss spectrum, that's possible, and the plural scattering correction will still be done because it can be done with a log ratio based approach in the log deconvolution or log convolution approach. We have the low loss spectrum. Yeah, it works just fine. The one thing to be mindful of is if you try to map things that are in the low loss spectrum, often you use the dynamic range of the detector for the 0 loss peak. So you have to be more mindful of the signal to noise ratio in ionization edges that are in the low loss spectrum if the 0 loss peak is there also. But there are ways to do the acquisition just fine. So you can do multiple passes and things like that to get around that. But it's just select the low loss spectrum add elements just as you would to the high loss, and the workflow is the same essentially.
Okay, perfect. Yeah, and then you just put the maps together because they're pixel by pixel registered, the low loss and the high loss. Yeah.
Exactly.
Let's see. There's a few other questions here, and I'm not entirely sure how to. Hang on a second. Actually, there was one question early on, which I partially answered in the chat, but in terms of doing quantification with noisy data, there's a tool for doing background smoothing in the map creation in the quant palette. Do you still have your DigitalMicrograph open, Liam? Could you show where that setting is in the map palette?
Is it here?
Yeah, under mapping. Yeah.
Yeah.
So yeah, so typically we do some background smoothing around each pixel to reduce the noise, and by default that's set at 1 pixel, which is relatively minor smoothing. For a more uniform sample that might be more noisy, you can turn up the background smoothing in this region. What it actually does is it smooths together the R value, the exponent of the power law, but then it still does pixel by pixel fitting of the amplitude of the background. So it does have a chance to do some improvement in the fitting and in the mapping, because there's a lot of redundant information there. Actually, not to steal your show here, Liam, but there was also this just reminded me, in a lot of cases for noisy data, especially if you have a counting camera like the K3 or the Stella, applying PCA noise reduction is often a really nice strategy. And we have a built-in function for that. And I think Liam had recently had a nice video talking about how to apply PCA. We'll send out the link to that video.
Yeah. So that's in this one in DataFit. So there's a MSA analysis tool, which you've got some buttons here. That's actually, as Ray said, it's in another webinar that I didn't list on my slide, but you can find it on the YouTube channel.
Yep. There was one question also about the DigitalMicrograph COVID version. So when COVID started, we've been sending out a series of versions for offline analysis based on that includes licenses that would normally be a charged option. That has recently been extended for another 3 months, I believe, and it should be on our website now. You just need to download the latest installer and just rerun the installer to get that extension for the EELS plugin. A lot of the features, even without the COVID version that Liam was showing, are available with the totally free offline version. In particular, fitting of edge shapes and fitting of regions of interest with multiple linear least squares fitting is part of the free package. It's not as convenient as the quantification, and the quantification dialog adds a lot of value, but there are ways to do it with the free version. Let's see, I think we have time for one more question. Someone was asking particularly more about the iron 2+, 3+ separation. Yeah, I think maybe we don't have quite enough time to go through all of that. how to create the maps. So your standards-based quantification webinar would give you a step-by-step process of actually how to create the individual maps like they did in that paper from our friends in China with the linear dust sample.
Yeah, I think one of these would be the best to use for a kind of a recipe. So you need to import the standards and then use them for the mapping.
Yeah.
I guess I could just, I'm not going to map it, but like, so the it's quite easy. You just need to import the standards. So follow how to use, follow the video, and then if you want to, you can see like subtly there's a little 2 here in my copper. So for copper, I have I'm using a standard for copper, but I'm using 2 standards. So you have this multi-selection way of doing that. But yeah, like that's done step by step in, I'm not sure which link it is. I think it's the top one, but it's about 10-minute kind of walkthrough on how to import the standards from whatever you want, and then how to use them for processing or mapping. It's pretty straightforward.
Yeah, but it is critical to account for pleural scattering, especially when you're using external standards like you might download from a database or from a different sample that you're using. Great.
Yes.
All right, so I think we're just about out of time here. I'm going to try to finish off at 1:45 to give everybody a chance to get started with their morning.
Okay.
So yeah, if there's not any other words of wisdom, Liam, I guess we just thank everybody for their attention. If we didn't get to your question already, I'll send out some email on that. I have some links for some people here in the questions, some papers that might be useful about low loss or very extremely low dose EELS on polymer samples. Which is another really nice example of what you can do with standards. Any
Nice.
parting words of wisdom, Liam?
I don't know. I think we're pretty covered. So
All right.
yeah. So I think this is a really great way to do EELS, this standards-based quantification. I think the combination of the plural scattering correction and being able to do phase separation and oxidation state mapping make that like a very useful tool. So it kind of, most samples are not uniform thick or infinitely thin. So that plural scattering correction is really key to being able to do like most work. It's really great. And yeah, just wanted to thank everyone for signing up and attending. It was fun to present, and enjoy the rest of the day, everyone, and catch you all another time.
Thanks.
Thanks.